Right. In this section, we are going to talk about how do we physically store these binary numbers or do some operations with these binary numbers. Now, in order to store the binary numbers, we need registers or the cells first of all. If you want to store a single bit, you need to have a binary cell. When you combine or group of these cells, we get a register. These registers can be 4 bits, 8 bits, 16 bits, 7 bit, 5 bit, doesn't matter. But generally, we are having the powers of 2. So grouping them, we are just having a register. And the terminology is a binary cell. It can be a two-stable state, 1 or 0, stores 1 bit of information, and which we are going to see later on. We store them in a flip-flop circuitries or a capacitor or ferrite cores. A register is a group of binary cells, so depending on the architecture, it can be 16, 34, 32, 64, and so on. And the register transfer is one of the major operations in computer architecture. In order to perform the operations with the binaries, we are actually physically needs to put into the register, and register will do the rest of the operations for you according to the CPU commands. So here are the simple example over here, where we have got the memory, input, output, and the CPU in between, which is the control logic over there, where we have got a control unit and data pad. So when you type in something from the keyboard or you some operations with the mouse or the microphone and so on, that goes into a CPU and then into a memory and so on. These are all working with the registers. So register needs to be in place in order to carry the data through the data pad and into the memory. So for example, when we type John from the keyboard, now each of these letters are going into a control and as an 8-bit cells. So 8 cells over there, and then that will be divided into 4 different letters, J, O, H, N, and then that goes into the memory unit. So each of these J, O, H, N is represented in individual cells or registers inside of a processor unit, which then will be stored in the memory register. And if you look at a typical operation with the load store machine, which is one of the most common and the major component of the digital system, we have got the memory unit on one side and we have got the processor unit on the other side. And if you want to perform any operation like arithmetic or logical operations, we have to load data from outside into the processor unit. It can be from memory or it can be from IOs, and then we perform the operation and store in another register. So first, we have to load the data into the two main registers in the processor unit, then we do the operation over here, and then we write the result to another register. So in load store machine, let's say load R1, we have to load register 1 with one of those operands from the memory unit by giving an address as well. So we have to specify the address. This is just giving an example. Then load R2 from the second memory unit, then operand 1. Now we have got two registers filled out, and we have to do an addition operation because it says add R1 and R2 and store it in R3. So this is going to be stored in R3 and result is written over here. Then say store data R3. So we are going to get this data from R3 and store it back into the memory unit. Okay, as you can see, we have got the binaries, but they're all inside of a register. So we cannot do any operation without these physical registers and without these physical addresses. Okay, so this is what we need to know. I'm not going to go into the details of this in this course, but we are going to cover these in another course, 347, in the third year course. So you just need to know that we have got registers, and if we want to do some operations, we have to use these registers. Right, so the next thing, or let's say the last part of this chapter, or the last section of this chapter, is the binary logic. Now, we talked about the binary in general, the numbers, now we need to talk about the logical side of it, because we talked about the arithmetic operations, but we didn't talk about the logical side of it. Now, binary logic is important, and we are going to use this a lot in this course or in any other area of digital design. It's really important, and we have to understand them. Now, first, let's give a start with the definition of the binary logic. It consists of the binary variables, set of logical operators. Okay, A, B, C, X, Y, Z, and we have got three basic operations: AND operation, OR operation, and NOT operation. Now, if you do remember from the introductory part of this chapter, which we mentioned or talked about getting from the transistor level into the gate and logical level or logic block level, this is where we start to talk about it. Okay, so logic operations, actually the logic gates like AND or NOT gates, that we have got a transistor or switches inside of it that we need to perform some operations. So let's start with the first one, which is known as AND operation. Now, AND operation or AND gate, we call it. What is AND gate? AND gates, as we already mentioned that they are like a physical switches, let's draw AND gates. AND gate is like two switches in series. Okay, and again we have got the battery and we have got the bulb and so on and so forth. So this is switch A and this is switch B. And in order to show the operation of a gate, we use truth tables. So A and B are the inputs, and we have got the bulb as a Y, as an output. So if we have two inputs, that means we have got four possibilities: when both are off, when B is on, when A is on, or when both are on. And we have to check the condition for each state. Now, when both are off, so when we want to have the current going through that, as we are not closing the switches, the bulb is not going to turn on. So that means output will be 0. Now, when A is 0 and B is 1, that means we are closing B over here. Now, what will happen? As A is open, it's not closed, that means the current will not pass through. It will stay over here. So that means, again, the bulb will be off. Now, if we change that, so this one is closed, but this one is open, the current will travel up to here, but it's not going to travel down to the bulb. Again, it's going to be 0. Okay, so when both are on, that means both switches are closed. At this point, the bulb will be on. This is known as AND function. So when both switches or inputs are on, output is on. And the way we represent this function is y is equals a dot b, or y is equals ab. Both are acceptable. And the symbol for AND function is a, b, and y. Okay, so this is how we represent the AND function. Now, another important one is OR function or OR gate. Now, OR gate is like similar operation, but switches are in parallel. Okay, so it's going on to the both of those. Again, the bulb, the battery, and so on. So A and B again. Now, if we derive the truth table one more for OR function, 4 possibilities again. Now, when both are off, again the bulb will be off. Nothing will travel down to the bulb. When this one is on, sorry, the B is on, and A is off, we are allowing the current to go from the B to down to the bulb. So that means it's going to be on. Or if A is on and B is off, that means the current will travel down from A, so this will be on. If both are closed, that means either way it goes, it's going to be 1. Okay, so we can say that this is A or B. So Y is equals A or B. Either A is 1 or B is 1, output will be 1. So we just say where it is valid. And the symbol for OR gate is A, B, and Y in this case. So this is AND operation and OR operation. We also have NOT operation. Now, NOT operation, or NOT gate, or inverter. Now, if you do remember, in CMOS, we have got two types of transistors, PMOS and NMOS. I'll do this transistor level explanation. So we have got PMOS, where it's going to turn on when we apply 0 volts. And we have got NMOS. When we connect them in series, one side on the supply and the other part to ground, and we have got input A and we have got output Y. Okay, now if I apply 0 volts here, or logic 0, that means this will be on, this will be off. Now, what does that mean? We are actually allowing the current go from VDD. So there's a small capacitor over here, which is going to charge it. Okay? So it's going to be charged. Now, as this is charged, that means the output is going to be VDD as well, which is equivalent to 1. So this is actually telling us when we have got a truth table, when input is 0, output will be 1. Now let's switch it. When we change this input to 1, then it means that this one will be on and this one will be off. So whatever we have got as a charge, it's going to be discharged to the ground, short circuit. So that means it's going to decay and this is going to be 0. Okay, so that means when input is 1, output is 0. And this is invert operation. And the symbol for it is a triangle with a bubble. Bubble always represents invert function. So A and Y. These are the three most common gates that we use in logic design. We are going to see some other gates in the following chapters. So AND operation, once again, represented by dot, x dot y, y dot x. It's always going to give you z. So they both needs to be 1, so the output can be 1. OR operation, either of them is 1, output is 1. And NOT operation, as you can see, where if the input is 0, output is 1. If the input is 1, output is 0. So generally, as a representation, either we use A prime like that, or we just say A bar. Okay? And this is a representation for it. So in order to show the operation, we use the truth tables as I already done it. AND operation, when both are 1. This can be 3 input or 4 input as well, but I'm just showing the simple way of it. 3 input, 4 input is not going to matter. They both, 3 input has to be 1, so the output is 1. Or either 3 of those is 1, then the output is 1. But for NOT, it's always 1 input. And I can demonstrate AND and OR function using the same thing that we have got battery and the bulb. When one of those is closed, bulb is off. When both are closed, bulb is on. If one of them is off, again, bulb is off. And over here, if either of those is on, the bulb is on. And this is what we are representing here. Okay, so We can also say that the binary logic, as we already mentioned before, there's a transition limits. So when we are transitioning from one stable state to the other one, there's an undefined portion as well. We are not accepting as a valid logic signal. So either logic 1 or logic 0, which is generally 3.3 volts, maybe less now with the naive technology, but the logic 0 is always grounded or 0 volts. And we can also represent the binary logic with the timing waveforms. X and Y's are the inputs, end function, OR function, and the invert function can be represented with the timing waveform. So 0, 0, end function is 0, 1, 0, end function is 0, but OR is 1, 1, 1 is both 1, 0, 1, and so forth, so on. So again, as I mentioned, we can have 3 inputs or 4 input gates, but the functionality is not going to change. If all are 1, then the output is 1 for end function. If either of them are 1, output is 1 for OR function. Now, as we are coming to the end of this chapter, we have got some exercises over here, which we are going to do it together during the live session. Thank you very much for listening. If you have any questions about this chapter, please note them down and feel free to ask them or discuss about it during the live lecture. Thank you.